Welcome to the deep dive. So, today we are going straight into the deep end of organic chemistry.
We really are.
We're focusing entirely on one crucial molecule, benzene. We're going to sift through chapter 25, pull out its structural secrets, the rules of its reactivity, and, the chemistry of its most important derivatives.
That's the plan. Benzene really does dictate its own rules, and you have to understand why. We'll start with that unique structure, the thing that gives it so much stability.
Okay.
And then we'll see how that stability forces it into a very specific type of reaction electrophilic substitution before we finish with phenol, where, well, just adding one little hydroxyl group changes absolutely everything.
Let's start right at the beginning then.
Okay.
C6H6, benzene. It's a colorless liquid, was a really vital solvent historically, but we should probably mention the downside.
Oh, definitely. It's a highly toxic carcinogen.
Yeah.
And it can absorb directly through the skin, so it's powerful stuff you need to handle with care.
And its simple formula, C6H6, that puzzled chemists for decades, didn't it?
For decades. This was a huge mystery in the 19th century. The famous breakthrough, of course, came from Friedrich August Kekulé.
The dream, right. The snake.
Exactly. The legend is he dreamt of a snake biting its own tail, and that's what led him to propose the initial cyclic structure.
So Kekulé is drawing the hexagon with, the three alternating double bonds. It was genius, but it hit a pretty big roadblock.
A major one.
If it really had alternating single and double bonds, the structure should have been, distorted. So why was his idea inconsistent with what people were actually observing?
Well, because when you measure benzene, it's perfectly planar and perfectly symmetrical.
Okay.
If you have alternating bonds, you'd expect short double bonds and slightly longer single bonds. You'd see a lopsided hexagon.
And they didn't.
They didn't. What chemists found was that all six carbon bonds are exactly the same length.
And that length was the key.
It was the smoking gun. The length is precisely intermediate between a single bond and a double bond. That uniformity just proves the structure can't be alternating single and double.
Yeah. Right, so what's the modern bonding model? The one that finally solved this mystery and explains benzene's famous stability?
It all comes down to the electrons being shared evenly. It's a phenomenon we call delocalization.
Delocalization.
So each of the six carbons is spear-2 hybridized. That forms the flat hexagonal frame with perfect 120-degree bond angles. And that leaves one spare electron on each carbon sitting in a p orbital.
So you have 6 p orbitals, one sticking up from each carbon, all ready to bond.
Precisely. But instead of forming 3 separate localized double bonds, like in Kekulé's drawing, these 6 p orbital electrons overlap sideways, above and below the entire plane of the ring.
So it's not 3 pairs, it's one big system.
Exactly. They're shared equally among all 6 carbons. This continuous shared system of delocalized pi bonding electrons, that is the source of its incredible stability. It's just a supremely comfortable state for the molecule to be in.
And once you get that structure, naming the compounds that come from it seems like the next logical step. What are the key names we should all know?
You really have to recognize the common substituted ones. So chlorobenzene, nitrobenzene, phenol, and phenylamine. And then when you have multiple groups attached, you just number the ring to give them the lowest possible numbers.
Like in 2004-6 tribromophenol.
Exactly like that.
So with that immense stability of the delocalized ring, what's the golden rule for how benzene reacts?
The overriding principle is this. Arenes almost always undergo electrophilic substitution.
Substitution, not addition.
Never addition if they can help it. They absolutely avoid the typical reaction of alkenes electrophilic addition because adding something would destroy that precious 6-electron delocalized system.
So you swap a hydrogen for something else.
We swap. That's the only way to maintain that high stability.
Okay, let's walk through the classic example then. Halogenation. Say, adding bromine. What do we need to make that happen?
You need bromine, Bedger-2, but you also need a catalyst. And this catalyst is crucial. We call it a halogen carrier, something like anhydrous Al-Br3.
And why is the catalyst so important here?
Because it essentially acts like a magnet. It reacts with the bromine molecule and polarizes it so intensely that it effectively creates a superelectrophile, the positively charged Br+ ion. Benzene won't react with a weak one.
And then that superelectrophile attacks the ring. Can you walk us through the mechanism? How does the ring manage to keep its structure?
It's a 2-step process, and it's all about a temporary sacrifice. First, the electron-rich benzene ring attacks that strong Br+ electrophile.
Okay.
This breaks the delocalization for a moment, creating this unstable intermediate with a positive charge. But the molecule immediately fixes that.
Wow.
In the second step, the carbon where the bromine attached, it sacrifices its hydrogen atom. The electrons from that carbon-hydrogen bond snap back into the ring, and poof, the stable, delocalized six-electron system is instantly restored. A hydrogen is swapped out, and stability is saved.
That's very clear. Now, what if we have something like methylbenzene? The source material says the conditions can completely change where the reaction happens.
This is a huge point for predicting products. It's all about conditions. If you use the catalyst, the LCl3, you get ring substitution. The electrophile attacks the ring itself.
Right.
But if you switch the conditions, if you use UV light and heat instead, you get a completely different mechanism. It becomes a free radical substitution that only targets the alkyl side chain, leaving that stable ring completely untouched.
So with chlorine and UV light, you'd get...
Chloromethylbenzene. The reaction happens on the methyl group, not the ring.
Let's move on to nitration, adding an NO2 group. I know this one requires some pretty strong acids.
It certainly does. For nitration, the electrophile you need is nitronium ion, NO2+.
And how do you make that?
You generate it by mixing concentrated nitric acid with concentrated sulfuric acid. The key is that the sulfuric acid is the stronger acid, so it protonates the nitric acid, allowing it to lose water and form that super reactive NO2+ ion.
And then you reflex that with benzene.
You do, usually with just some mild heat, and you form nitrobenzene.
Now, once you have a group on the ring, that group then dictates where the next substitution goes. This is the whole idea of directing effects, right?
Absolutely. And it's essential for planning any kind of synthesis. Groups on the ring are either electron donating or electron withdrawing.
Okay, what do the donating groups do?
The electron donating groups, like methyl or OH or NH2, they activate the ring. They pump more electron density into it and direct the next electrophile to positions 2, 4, and 6.
And the withdrawing groups?
They do the opposite. Electron withdrawing groups, like the nitro group, NO2, they deactivate the ring and they steer the substitution to positions 3 and 5.
Yeah.
So, for example, if you nitrate nitrobenzene again, you end up with 153 to nitrobenzene.
We should probably also give a quick mention to the Friedel-Crafts reactions.
We should. They're the main way to add carbon side chains. Friedel-Crafts alkylation adds an alkyl group, and acylation adds an acyl group. And just like halogenation, they need that LCl3 catalyst to help generate a positive carbocation to attack the ring. The mechanism is really the same.
Right. And finally, let's cover the two big exceptions to this substitution rule: oxidation and hydrogenation.
Okay, so alkyl side chains, which are normally super unreactive alkenes, they become reactive when they're attached to the benzene ring. Any alkyl group can be oxidized all the way down to a carboxylic acid.
So methylbenzene becomes...
Benzoic acid. You just reflux it with alkaline potassium manganate 7. The second exception is hydrogenation. If you really want to force benzene to undergo an addition reaction, you can, but you need drastic conditions: high pressure, heat, and a nickel catalyst to finally break that aromaticity and form cyclohexane.
Let's shift gears then to a really key derivative, phenol, C6H5OH. It's a solid, slightly soluble in water, but its most surprising property is its acidity.
Definitely. Its preparation is pretty involved, actually. You start with phenylamine and react it with nitric acid under cold conditions to form an unstable thing called a diazonium salt.
And then?
You just gently warm that salt up in water, and it hydrolyzes to produce the phenol, along with HCl and a bit of nitrogen gas.
Okay, but the acidity, that's the really interesting part here. If you look at the pKa values, ethanol is about 16, water is 14, but phenol is down at 10.
Which means it's a much stronger acid.
A dramatically stronger acid than a simple alcohol. So why? Why does sticking an OH group on a benzene ring suddenly make it so much more acidic?
It all comes down to the stability of what's left behind, the conjugate base, which we call the phenoxide ion.
The C6H5O-.
Exactly. When phenol loses its proton, that resulting phenoxide ion is incredibly stable. And that's because the negative charge on the oxygen doesn't just stay put on the oxygen.
It doesn't stay bottled up, so where does it go?
It spreads out. The lone pair on the oxygen overlaps with the whole delocalized pi system of the ring. The entire ring helps to bear that negative charge.
So it's delocalized just like the pi electrons.
Precisely. That delocalization stabilizes the phenoxide ion way more than, say, the ethoxide ion from ethanol, where the charge is just stuck on that one oxygen atom.
Right, so because the product, the phenoxide ion, is so stable, the equilibrium is pushed further to the right, favoring dissociation. That makes it a stronger acid.
You've got it. And that acidity shows up in its reactions. Phenol, being a weak acid, reacts with strong alkali, like sodium hydroxide, to form a salt, sodium phenoxide, and water.
And what about substitution into the ring? Does that OH group also change how the ring itself behaves?
Oh, changes it dramatically. The
Yeah.
OH group is a powerful electron-donating group. That lone pair on the oxygen just floods the ring with electron density, making phenol far, far more reactive towards electrophiles than plain benzene.
So it activates the ring.
It superactivates it, and it specifically directs any incoming electrophiles to the 2, 4, and 6 positions.
And that increased reactivity must mean we can use much milder conditions. Let's compare bromination one more time.
Great example. For benzene, you remember, we needed pure bromine and a strong catalyst.
Right.
Phenol, on the other hand, reacts instantly with something as mild as bromine water at room temperature, no catalyst.
And what happens?
It immediately decolorizes the orange solution and forms a white precipitate of 2,4,1,6-tribromophenol. 3 substitutions happen just like that, with almost no effort. It's a testament to how much that OH group activates the ring.
Wow. And I'm guessing the same thing applies to nitration, milder conditions.
Absolutely. Benzene needs concentrated acids and heat. Phenol will readily nitrate using only dilute nitric acid at room temperature. It's a completely different level of reactivity.
So if you were to summarize this for someone, what are the key takeaways they absolutely need to remember?
I think there are 3 main insights. First, benzene's defining feature is its stability, and that comes from its 6 delocalized pi electrons. That's idea number 1.
Okay.
Second, that stability dictates its main reaction.
Huh.
It will do electrophilic substitution to preserve that ring. And finally, number 3, adding an OH group to make phenol just. It fundamentally changes the molecule. It boosts its acidity because the phenoxide ion is so stable, and at the same time, it makes the ring hyper-reactive towards electrophiles.
And what stands out to me, is how those subtle differences in conditions are what give chemists real control. The choice to use a catalyst versus just using UV light. It completely shifts the chemistry from the ring to the side chain. It just shows how nuanced controlling these reactions can be.
That's a critical takeaway for anyone studying this.
Thank you for joining this deep dive. We'll catch you next time.